Hello and good afternoon, everyone, and welcome to our webinar. Today, we are going to talk about reliability. My name is Laura Frisk, and I'm the CEO of Trellick. And as I said, today we are going to talk about reliability and how you perform reliability analysis and why performing reliability analysis is so important. So this webinar is about 45 minutes. And if there are any technical issues, you can also listen this later from our YouTube channel. Here's the outline of the webinar. I will start with a very short introduction and tell a bit about Trellick, so what we do and what is our background and why this is an interesting area for us. Then I will talk about why reliability analysis is so important and why it's important to take that into account no matter what kind of product you are developing and what you are doing. Then I will very shortly talk about why products fail and what kind of issues we are facing there. So when do products fail and what are the reasons for this? I will next talk about reliability goals and mission profiles and also a bit about testing, so how we analyze reliability. And finally, I'm going to talk about reliability prediction and reliability data. And lastly, give a summary. So then to our introduction. So in Trellick, we are a Finnish company based in Tampere in Finland. And we work with different reliability topics. We mainly work with electrical engineering and electronics, but also with mechanical materials and their aging. So quite often in our reliability projects, we deal with reliability of new products and how that needs to be determined. And in addition, we deal a lot with materials, how they age and how to study them. Also quite often in our different projects, we are dealing with products which already are in the field, but there are some issues with their reliability and we need to quickly analyze how they failed and why did they fail and how we can fix things. So we offer both experimental studies and also consultation. So here is a quick overview of our services. So as I mentioned, we do reliability analysis from very beginning of test design to actual testing and modeling of failures, and we do failure analysis, material analysis, and we also work with electronics assembly, mainly for new products such as wearables and interconnections for difficult applications and so on. So, but then to our topic. So why is reliability so important and why we need to consider this? Reliability is actually quite often considered very important, but not necessarily considered in enough detail. And why is it considered important is that because the expenses due to poor reliability can be very, very large and considerable. And this, of course, is an issue. And in addition, the problems with reliability quite often cause problems and delays in product development, especially if we realize rather late that there is a reliability problem and we need to go back and start from the beginning. This can mean a very large delay and cause lots of problems. So we need a systematic approach to make sure that the reliability is good and the product, all the kind of factors affecting our reliability are considered. Now, quite often when we talk about reliability costs, we talk about warranty costs, which are easy to determine and they are easily analyzed, and that's why they are mostly considered. However, there are lots of other costs too. And when we have a failure, we need to analyze why the thing failed. And this can be very expensive. It can be very time consuming. And also we need to use expensive techniques to analyze why failures happened. We may have customer downtime. We may lose customers. Eventually we may have lawsuits. So this can be extremely expensive and also very bad for reputation. However, the problem with the many issues related to poor reliability is that they are not very easy to define. And this means that it's very easy to overlook them, not to consider them, especially when you are doing product development. You don't necessarily consider customer satisfaction or loss of reputation or how many hours you are going to waste when you need to go back and analyze why something failed. And this means that it's not quite often considered how much this will cost. But on the other hand, it's easy to analyze why, for example, testing costs, which can be also very high. And that's why it may be that the reliability is not considered enough during the product development. So one could say that the warranty costs are only the tip of the iceberg, and the actual costs due to poor reliability are a lot higher. So what does reliability mean? This is actually something which seems quite obvious, but may not be that. And people may have different ideas of what reliability means. Quite often, the definition used is that reliability is the probability that a product, system, or service will perform its intended function adequately for a specified period of time. So we need to know how long does our product need to function and what kind of conditions are we having so that we determine it to be reliability. And this also means that the product should function not only when we have manufactured it, but also during transportation, storage, and so on. And it's also very important to consider that different people may have different ideas what is good reliability and what should be reliability for different products. So this may also cause problems and sometimes be an issue, especially when you consider customers and manufacturers and how they view the reliability. Now, as I already mentioned, reliability can be very, very expensive if we realize rather late in the product development, okay, we have a reliability issue. And this may be a big problem. So for this reason, it is very, very important that we consider reliability as early as possible in the product development. And the reason for this is that when you start doing designing a new product in the early stages, for example, materials, components, and so on, they are decided. So if we choose poor material or poor components or just wrong kind of layout or whatever, it may be very, very difficult to change later, or it will be very expensive. So due to this reason, it is very, very important that the reliability issues are considered already when these decisions are made, because then it's easy to check, it's easy to fix if there is a problem. So we typically recommend testing already as early as possible. We work a lot with also with startup companies, and they quite often, for example, are very excited about their new product and want to do prototypes as quickly as possible. But there is a risk that then you need to go back to the beginning when you have done something which is critical from reliability point of view. Of course, this applies to all companies. So it is very, very important to consider reliability as early as possible. So then we go to the reason why products fail. So what is the reason for failures? No, there of course are lots of reasons for failures. We have lots of different products, lots of different materials and systems and so on. So there may be lots of different reasons. Quite often we are using bathtub curve to analyze failures, which is shown here. I have to say that this is not always valid. Quite often, actually, it isn't, but it's a kind of idealistic idea that in the beginning, we have a decreasing failure rate. And this is quite often a period where we have failures due to, for example, manufacturing problems, that there is a mistake in the manufacturing which causes part of the products to fail because they have some problems. After that, we quite often have a constant failure rate, not necessarily though. So as I said, this is idealistic view. Quite often it's something different, but and during this period, we quite often have failures due to, for example, misuse. So someone is using the product in a way it should not be used and it fails, for example, because we had too high temperature or too much mechanical stress or something like that. Or just a random event, which may be very, very difficult to prevent. And then when we have used the product for a long time, we start to have increasing failure rate due to wear and aging. So the components have issues. They have been used so long that they start to fail due to kind of natural reasons. So we have lots of different reasons for failures, and it is important, of course, to understand what kind of reasons we have and how to prevent the failures. So it is important to understand why they are caused. So as I already mentioned, we can have failures due to manufacturing, due to different issues. So it's important when we consider failures to consider all the stages of the product's lifetime. So we have manufacturing, for example, in electronics where we work a lot, there are lots of quite often high temperatures used in the manufacturing, and these can cause stresses to the structures, which later cause failures. And it is important to take these into account. In addition, we have, for example, transportation almost always. In this case, it's often mechanical stresses due to, for example, vibration, but also temperature, humidity, impurities, so on. And then we can have storage. For example, at the moment, we have one project where we have issues with storage and or caused by storage conditions which have caused corrosion. And this can be a major issue in some applications, especially if the storage is done in areas where the product is exposed to difficult environments. They might even be worse than the actual use conditions. So of course, then we have also use, which needs to be considered. So all the stages need to be considered when reliability analysis is conducted. And when we talk about failures, it is very, very important to determine what is a failure, because this is not always clear. Sometimes it's very easy to say that this product has failed. It doesn't function as it should. But this is not always the case. And especially when we are talking about very complicated systems, for example, a car, you can have some parts which work okay, some parts which don't, and then where do you draw the line for the whole product, for example? Has it failed or not? So it's not always very, very easy to do this. And you need to have a clear idea what is a failure, especially when we do testing. And quite often we test also subparts or even just materials. We need to be able to determine when a failure has occurred. So therefore, it's very important to determine what is a failure and what is a failure limit. And for example, I once worked in a project with adhesives where we had two different use cases. And one said that even 10% increase in the contact resistance of the adhesive we had, it was electrically conductive, was an issue and it was too much. While the other one said that, okay, 100 times increase, it's not a problem. So we always need to know what is a failure, and that is important that it's determined early and as clearly as possible. So then we go to reliability goals and mission profiles. And also testing about reliability. So we always need to have a reliability goal to know why we are testing and what we need to reach. So basically, our reliability goal should tell us how the product should operate, what is acceptable, what is okay, when is it still working as it should, and what kind of conditions do we accept, what kind of humidity or temperature range and so on, and for how long. So what is the use life, and also how many products are okay to fail. So because almost always there is a certain percentage of products which will fail. And so when you start to do reliability analysis, you need to know what is needed. Do you need to have, if you need to have 100% functionality, then you need to do a lot more testing than if you can accept a few failures. And why reliability goal is very important to determine is that with that, we can start to determine how much testing we do and what is good enough, so that we don't end up doing over engineering. So it's always a compromise, as is kind of here the picture is trying to tell that we have cost due to poor reliability, and then we have cost if we start to fix issues and kind of over engineer our product. So it's a compromise always, and the reliability goal makes it easier to reach this. Another important tool when we are doing reliability analysis is mission profile, if we can get one or something similar. So mission profile is a term we use for something which tells us what kind of stresses does the product face during its lifetime. So it can tell us that, for example, what kind of temperature is the product facing, and also kind of how long will it be. For example, that 25% the use will be above 50 degrees and then the rest below it, or what kind of humidities, what kind of impurities, and so on. So what kind of stresses will the product face? And it should include everything from the manufacturing to the use. And as I already mentioned, transportation and storage can be very important. And so it should include the severity of these stresses and how long. So this is, but there are different mission profiles. Sometimes you can get it, sometimes you don't get anything. And it's not very easy to do, and it depends of the product how easy it is to get this kind of information. Quite often we need to just approximate something or just kind of take the worst case scenario and go with that. But this is very, very good tool if you can get it, because you can use it to find good test methods. And also it's a good tool when you are trying to figure out why something failed, because it tells you what kind of environments the product has faced. So now when we have an idea and want to start to analyze the reliability, we need to do some testing. And for that, we normally use accelerated live testing. Basically, it means that we do testing of different things and try to accelerate it as much as possible. Now, the reason for this is that testing can be very, very expensive. It can also be very time consuming. So you cannot test for 7 years if that's the use life. So we need to do something a lot quicker. Normally, we are talking about weeks or months, but as short as possible is normally what we are looking after. And basically how we do the acceleration is by using higher stress levels than are seen in the use life. This could be, for example, mean higher temperature, which is very common, or higher humidity, higher level of impurities if we are testing corrosion. Or for example, for thermal cycling, if the product is 1 cycle per day, instead of 1, we do, for example, hundreds or maybe 50 per day, and then we can do the testing a lot quicker. However, before we start testing, it is extremely important to consider what is a good test procedure and what kind of stresses do we need to test. So when we are doing testing, and for example, with our customers, we always are discussing a lot about testing, and quite often many people want to use standards test, which makes sense because it's easier to report, it's easier to explain what you have done when you have used a standard. However, it is important to realize that there are, first of all, lots of standards, and quite often they are nowadays quite open. So that means that you can choose between many different conditions, for example, temperature ranges if you are doing thermal cycling and so on. So it is very important that when you do testing, you really consider what are the best conditions, not just to pick something someone else has used or from one standard. It is very important. It is also important that many standards have become very commonly used, although they have been originally developed for something totally different. This especially has happened in electronics. We see that a lot. And then you need to consider whether the test is still valid, whether it accelerates things that make sense. And this might not always be very easy, but it's very important to do this. Because if we use wrong test methods, we may end up thinking that the product is poorer than it actually is, and then do more work that even though it is already good. Or the other way around, which is probably worse, is that you end up thinking that the product is okay even though it isn't, and then when you start to use it in the field, you get lots of problems. So as I already mentioned when I was talking about mission profile, it's a very good tool to consider the test method. So if we know what kind of stresses the product is facing and what kind of environments it will be exposed to, we can use these to choose the right test methods. The aim of the testing is always to simulate the stresses observed in real life. And so this way, when we know what the stresses are, we can choose the best test methods. What is also important to notice is that normally when we test, we do the tests separately. So we can have separate tests for temperature, separate tests for corrosion, separate tests for mechanical, for example, vibration, and so on. This makes it a lot easier to analyze the results and analyze why failures happen. However, the problem is that from time to time, we have a combinatory effects of the stresses, meaning that we have two stresses which accelerate each other, make them more critical. And this can be an issue. So it's always important to also consider whether this could be possible, and is it important to test also these different combinations. For example, high humidity, high temperature test is probably one of the most used tests in electronics because of this, because it has been seen that this is very important combination. So here's the list of typical test methods. I'm not going to talk about these all, just to mention these. So we have thermal testing, which is very common. It's easy to do. Both high and low temperature are normally tested. Not always, it depends on the application. And here, of course, quite often the materials, for example, limit how high you can go. But there are also lots of models for thermal testing, which makes it an interesting and easy test method. However, what we quite often see is that thermal testing is not very efficient. So it can take a lot of time to get failures. And that's why we often use thermal cycling and shock tests, in which the temperature is cycled depending on the application from minus to plus 100, or depending, it can be very harsh or a lot milder. This is very efficient. It causes, due to thermal expansion differences, causes lots of mechanical stresses, and is, for example, in electronics, very, very good test. Then we have humidity testing, also very common, and corrosion testing, also widely used. Sometimes also we need to test other things, to test impurities, for example, dust and sand, and biological testing is very important in some areas. We also have mechanical shocks and vibrations. These are also very common tests, and there are lots of standards for these, and especially in car industry, for example, very important tests. But there are other mechanical stresses we use. For example, here is our bending tester, which is designed for flexible electronics in the picture. And then when we go to material testing, we quite often need to do different stresses. And for example, UV testing is very important with polymer materials. And also electrical stresses can be very, very important. So one test method also I want to mention is highly accelerated live tests, or highly accelerated stress tests, so HALT or HAST. And these are quite often used, especially in electronics. The aim of these tests is to use extremely high test conditions, which go way beyond the normal use conditions. And the point here is that these tests can be very, very fast. They can give results in few hours. But and they are used to increase the robustness of the product. It is, however, very important to notice that from time to time these tests can accelerate failures which are not meaningful and lead to incorrect improvements. So meaning that you do over design or change something which would not need to be changed. So this is something which is good to understand. So HALT testing uses temperature, vibration, and humidity, while highly accelerated stress testing deals with very high temperature and humidity. But I've seen both used very successfully. So they have also used, but you need to be careful when you're using them. Then last about testing is tailored testing, which is kind of a trend, has been for some time now in reliability engineering. So the idea here is that we tailor the test according to the product. So instead of taking a ready-made standard test, we actually design the testing according to the product using mission profiles and so on. The good thing about this is that we can have very accurate results if we know the conditions, but this testing may be very demanding to design and to do if we do combination of several stresses. But this may also give us very high acceleration without the problems related to HALT or HAST. So we are still dealing with realistic failures. Also, it's very, very difficult to do any prediction with these tests because there are no models or history data for this kind of tests. But they can be very, very useful, so I warmly recommend considering them too. And then finally about testing is we do lots of testing. So there are different tests, and they need to be done at different places of the product development. So we quite often talk about reliability testing and validation testing, meaning that with validation, in the end of product development, we just want to show that our product does what it's meant to do and is okay. With the reliability testing, it's something to assess the reliability. So this can be done in the beginning of product development and later after we have prototypes and so on. And the aim is to make sure that the reliability is good enough, and if not, check how things fail and fix it. Then in the end, we do validation testing to check that and show that our product can perform certain tests can survive. So these are normally, while reliability testing should always be conducted long enough to have failures, if possible. It's not always possible, but if possible. Validation testing is normally shorter, and it's a pass or fail testing, so you shouldn't get any failures. It's just important to realize that if you do this kind of pass or fail testing only during the product development, you may not get enough data to really analyze the reliability, and this is a risk for reliability analysis. Also, what I want to say about validation testing is normally that it's based on standards, it's based on requirements either from internal systems or from customers or by a third party. So sometimes you have tests you just have to do, and this of course needs then to be done. And as I said, both are needed, both are very important, but it's important to understand that they have a different kind of, the aim of these tests are somewhat different, even though same methods may be used. So after we have tested, or if we have problems in the field, we do failure analysis or root cause analysis. Both mean about the same thing. There are also some physics of failure analysis and so on. So there are lots of terms used here, and it depends of the person and their background what kind of terms they use. So the aim here is to find out why and how failure has occurred. And the point, of course, is that when we know why and how, we can check, do we need to do something to fix it? If it's a random matter, maybe it's not important, maybe we don't need to do anything. But if it's something which can be seen that it will cause lots of problems in future, we need to fix it. And there is lots of techniques we can use to conduct failure analysis. Sometimes it can be very complicated, sometimes it's very straightforward, but it depends on the application and what has happened. We have another webinar in the next week about failure analysis, so I'm not going to talk more about that. And I'm going to go to reliability prediction and reliability data. So when we do reliability analysis, we normally want to have some sort of prediction from that. This is especially when we are dealing with industrial processes. This is very, very important, or we are developing a new product. We need to know how long will the product survive and what is the probability that it will fail. This is very, very important, of course. And if we have, for example, test data, we can then use different methods and tools to analyze this, to make some sort of prediction or model to analyze when will the failures happen and maybe even how they happen. And these kind of models are normally based on different things. They can be based on material properties, on failure mechanisms, and different conditions. So we need to know what is the reason for failure to do this, and what kind of, for example, if we did testing and we are analyzing the test results, we need to know then what are the use conditions and what is the relationship between the use and the test conditions. Now, unfortunately, this is often relatively difficult. It's not very straightforward unless you have something which has been studied a lot and there are clear models and easy models you can use. And some structures and materials have this. For example, solder joints in electronics have been studied a lot. So there are lots of different models you can use to assess the reliability. But even there, actually, the problem is that you have lots of different models and you need to know which one to choose, and that's not always straightforward, and there can be some discussion in the paper about which one is the best. Unfortunately, often the situation is so that there is no clear model or supporting data you can use, and then you need to do assessment, maybe use something which is not optimal, and then you need to realize that there is a risk which is caused by this. But there are some models, for example, which have been commonly used in reliability analysis. I would guess that Arrhenius equation is the most commonly used. It's used for many different things, and I have a few slides about this. So here, the factor we are studying is temperature and how it affects the reliability. Another model which you can check, for example, is Peck and Lawson models. Here is both temperature and humidity are considered. This is also quite general. So, but it's one model which can be used in these cases. Then Coffin-Manson is very common for temperature cycling, fatigue failures of metallic structures. It has been very commonly used, and it's a basis, for example, for many most of the models used in solder joints, which I was talking about, because they are metallic structures and can be modeled like this. So Coffin-Manson is the one behind them. I also want to mention that you can also start to build just your own empirical model, so that you use the data you get, but that of course requires very good data, and typically when you want to do this kind of modeling, it would be very good to have measurements from different temperatures or different combinations of environmental factors. So this can make testing expensive and time consuming, which is a drawback of trying to get a good reliability model or prediction. So yes, the Arrhenius, which is relatively straightforward model, you can see the basic one here. The idea is that this has been developed originally for chemical reactions to study their rate, and the idea is that we have activation energy. So basically in the initial state we have something, and to reach the final state it needs to go through a state which requires a certain amount of energy. Now, when we increase the temperature, we have more energy, and the probability of this change from initial state to final state happening increases. And so basically the equation describes this, how this happens. So basically we need the activation energy to use this. And for example, for electronics, there is lots of lists where you can check what kind of activation energies have been given or have been found from studies to certain structures. But the problem may be that still the activation energy is not suitable, for example, for a new component which has a different materials or different structure. But this model has been, or equation has been used for many different things. For example, here is a diffusion, which is quite often can be studied using Arrhenius equation. But as I said, it's from time to time, actually it's quite common that you can see that Arrhenius is used for complex structures. And this is very risky, and it can give totally wrong results, because you need to be sure that the failure mechanism stays same. If you test at high temperature and then lower temperature, you need to be sure that the failure mechanism is the same. Otherwise, this is not valid anymore. So here's just a quick example. This is a degradation of polymer materials in which Arrhenius worked, actually, or this case worked really nicely. There was some error to our activation energy. So here you can see that 20% change in the activation energy actually decreased the time to 600 hours, so 1/3 from the original. So the risk here is typical to many models that you have a relatively small change in some value, and it can actually end up having relatively large change in the actual used life. So to do any kind of modeling or any kind of prediction, not really modeling, but prediction, we need good data. And this is very important for any kind of reliability analysis, is that we can get good reliability data. And there are several sources to do this. So testing, of course, what you do during product development is very, very important. And that's why we always recommend that, if possible, test as long as possible to see failures, because this also gives very, very important data. Then if your product is already in the field, you can probably get warranty data normally, or maintenance data. If it's a product which will be maintained, this of course is not always the case, and then it can be very, very difficult to get any data. And in some cases, when we have been talking about it, it can be very, very difficult to get any data at all. So if you are lucky, you can maybe get field failures after the warranty period. Normally this is very difficult. Or you can do additional testing during the lifetime of the product to see what happens. And quite often also history data from earlier product is very valuable. And literature data, and nowadays more and more simulation. So if we can do, for example, finite element analysis, sometimes it can be an excellent tool to add information to reliability prediction and understand where are the main problematic points which need to be studied, for example, where the mechanical stresses are concentrated. What I need to say about, well, actually it's the second slide about this, is the main data, of course, is the field data and then from the testing. And sometimes history data and literature data can be very, very important too. But field data is problematic quite often because it's difficult to get. And even if you can get it, it might not be very reliable. So in many cases, getting the actual failure times or how products fail can be very, very difficult. If you just have warranty data, it's highly censored data, and this needs to be taken into account when it's considered. I, from time to time, have seen analysis of warranty data so that it's not considered censored. And censored data means that only part of the products have failed and the rest are okay. So you need to consider that this is only a part of the products. So the failure times are, for example, for 10% and the rest are okay. And if you only analyze the failure data of the failure, it can lead to very incorrect results. So quite often the field data is not very good quality, and even if you have a system, which I highly recommend to consider having a system where you can collect good quality field data, but even in this case, it might not be that the people who are collecting the data are not really doing it in enough detail to have good quality data. This is why laboratory testing may be very valuable too and should be done. The point here is that we can have controlled data because we know exactly what has been done and what kind of products have been tested. Of course, here then the problem may be that it does not totally correlate to field data. So both are very useful, but I want to emphasize that it is very, very important to have good data when you start to analyze the data, especially if you do prediction. Okay, so this was my last slide, so I will give a quick summary. What I want to emphasize is that the reliability needs to be considered throughout the product development and manufacturing, especially in the beginning. So not just in the end, when everything has been decided. It is very, very important to do it earlier and check and test and analyze and see what are the critical points and whether they need to be fixed as early as possible, so it won't be very expensive to do the changes. And there are lots of reasons for failures, so it is important to consider the stresses from all different parts of the life cycle. Sometimes it can be just, for example, as I mentioned, storage conditions, which are the critical, or transportation, which actually causes lots of mechanical stress, and then is the reason. So it's important to consider also these. And there are lots of tests and lots of standards for tests available. So it is important to consider carefully which ones are meaningful, because testing is normally quite expensive. So that you don't end up doing lots of tests repeatedly. And clear goals, and if you can have mission profile, they help a lot to determine which are the good tests and which ones to use. And there are lots of models for reliability prediction, but it is very important to consider how reliable the model is. How can you trust its results? Okay, so that was my last slide. Thank you all for attending. As I mentioned, we have 2 other webinars in this series coming. There's a failure analysis in the next week, and the week after that, material characterization is discussed by Sanna Lahokallio from us. So please join us then again, and thank you again for joining us.